Welcome back to our series on statistical methods. I'm Mark Ledbetter. This is lecture 18, and this is part 10 of chapter 3, and we are going to finish up the talking about the random effects model. In the next video, we will do an example using R code. So let's get started. In this video, we want to discuss how to estimate the model parameters. So this is a random effects model, and so we're going to be interested in estimating the variance components, not the treatment effects, not the means of the individual treatments. Remember that we are not interested in the individual treatments that we've chosen. They're just randomly selected from the population of treatments. So there's nothing really special about those that we have chosen. They have just occurred by random chance, so to speak. And because of that, we don't do any contrast. We don't care about, contrast. We don't care about treatment means or treatment effects. What we care about are the variance components. So we want to estimate these variance components. And remember, that's what we used for the hypothesis. We hypothesize that the sigma tau squared is equal to 0 versus that it's greater than 0. So we're going to talk about the Anova method, and this is a method of moments procedure for estimating parameters. It has some advantages and some disadvantages. The advantages is that it is simple. It uses the Anova table to estimate sigma squared and sigma tau squared. It does not require normality. This is very advantageous. And it doesn't require normality because it is a method of moments estimation technique. It uses the best unbiased estimators for sigma squared and sigma tau squared. So that's the good news. The bad news is that it can produce a negative estimate of variance, and this is not possible. Remember that sigma of any variance is greater than or equal to 0, and this is the standard deviation, sigma. And then the variance, which is that squared, definitely can't be negative. So this could be very embarrassing. You need to be on the lookout for this and make sure that you don't report a negative variance to your peers, because they will point out that that is not possible. And if they don't understand this method, they may say you've made a mistake, when in fact you may not have. Okay? So if you get a negative estimate of the variance component, you have a few options here. One is re-estimate using a method that always provides a positive or non-negative estimate. We could also, or instead, re-examine the problem and verify that a straight line model is correct or incorrect. Okay? If it is nonlinear, then you'll need to rerun the problem using the correct model. The third option is not a very good option, but some people do use it, and that is we use the negative estimate as proof that the variance is really 0 and that the negative value just occurred because of sampling error. Okay? For most people who don't understand statistics in the program, they're not, and how you calculate these estimates, they're not going to understand this. So this is really the least desirable option here, okay? All right. Now, here are the parameters and their estimates, okay? So the first parameter is sigma squared, and that is estimated using the MSE. The next estimate, I had a typo here. It's sigma squared plus n naught sigma tau squared. And that is MSTRT. So the MSTRT is a combination of the two variances. Okay? And then if we want to solve this for sigma tau squared, what we have is we have sigma squared plus n naught sigma tau squared. And I'm going to put hats on these as estimates. That's equal to the MSTRT. Now, we've already said that sigma hat squared is sigma hat squared is equal to the MSE. Now, this is the parameter, so the parameter is not a hat, but the estimate, MSE, is equal to sigma hat squared. Okay, So I'm going to solve for sigma tau squared, sigma tau hat squared. And so I'm going to add or subtract sigma hat squared from both sides and then divide by n naught. So what I'm going to, what I'm going to do is I'm going to get n naught sigma tau hat squared equals mstrt minus sigma hat squared, which is equal to mstrt minus mse. And then I need to divide by n naught, and so I have sigma tau hat squared equals mstrt minus mse over n naught, which is exactly what we have here. Okay, now n naught, if we have a balanced design, then that's simply n, because n1 equals n2 equals na equals n. But if it's not balanced, then we have a minus 1 times the sum of ni from I equals 1 to a. Now, that is equal to capital N, by the way. Okay? So we take capital N minus the sum of ni squared divided by capital N. So this is a modification of n based on unequal sample sizes. All right, so this is if it's unbalanced design. Okay. So let's look at a confidence interval for sigma squared. Okay, so the assumptions are that the observations are independent. Now, I don't know why I haven't cleaned this off. Okay, but oh yes, so I need to clean all of this off. I remember now. Okay, we'll do the derivation. Okay. So, the assumptions, the observations are independent. So we're going to verify that. How you get independent observations is randomizing the order of the producing those observations or creating those observations. So we can verify that using a plot of residuals versus time or the order. And I see example 1 for the method, but we're also going to show this in example 2 for the random effects in the next video. Okay? And so the observations are normally distributed. That's another assumption. And again, we need to verify that, and we can use the QQ plot of the residuals to do that. Assumptions 1 and 2 imply that n minus a times mse divided by sigma squared has a chi-squared with n minus a degrees of freedom. Because of that, we can figure out the confidence interval. So as soon as we know how it's distributed, we know that this random variable between chi-squared with 1 minus the critical value for 1 minus alpha over 2 and the critical value of alpha over 2, the difference between those is 1 minus alpha. Why? Well, let's look, if I can draw it decently, let's look at the chi-squared distribution. It's a skewed distribution, and 0 is here. And so if we look at this by the definition of the critical value, if this is chi-squared 1 minus alpha over 2, then the area to the right is 1 minus alpha over 2. Whatever the subscript is here, this is the area to the right or above it. That means that the area here or below it is alpha over 2. And likewise, if we have chi-squared alpha over 2, that means that the area above that is alpha over 2. So if the area above that number is 1 minus alpha over 2, and this area is alpha over 2, then the area here has to be 1 minus alpha. Okay? So we have 1 minus alpha over 2. Yeah, so this would be 1 minus alpha. If we subtract another alpha over 2 from this, we have 1 minus alpha over 2 minus alpha over 2 equals 1 minus alpha. And so once we've written this probability here, this probability statement, and notice that this value is smaller than this value, okay? So this might be, for a 95% confidence interval, this might be chi-squared 975, and this is chi-squared 0.025. This 0.025 critical value is bigger than the 0.975 critical value, okay? All right. So let's clean this up and do our derivation. Once we have this, what we want is we want to isolate sigma squared by itself. And we want it on the top, so to speak. We don't want 1 over sigma squared. That's not the confidence interval that we're looking for. So what we're going to do is we're going to reciprocate all of the numbers. Take the reciprocal of. Now remember, if I have 1 over 3, so if I have 3 is less than 5, that's true, but 1 over 3 is going to be bigger than 1 over 5. If I divide by a smaller number, I get a bigger number. If I divide by a bigger number, I get a smaller number. So when I invert these or take the reciprocal of these, I have to switch the signs here. And I'm going to reorder them because when I take 1 over this, that's going to be bigger, not smaller than this quantity. So I'm going to move it over to here, and then I'm going to take this and I'm going to move it over there. So I'm going to switch the order so that I keep them in ascending order. We like to start with the smallest value, then this value, then the largest value, going in this direction, the same direction as the number line. Okay. So that's what I'm going to do. So that's my first step. I'm going to have 1 over the larger value, this value, chi-squared alpha over 2 n minus a. And then I'm going to have sigma squared over n minus a times the MSE. And then I'm going to have 1 over the chi-squared 1 minus alpha over 2 with n minus a degrees of freedom. And that is still 1 minus alpha for the probability. Now, I'm going to multiply all 3 portions of this inequality by the denominator in the middle, which is n minus a times MSE. So this is going to give me the probability of n minus a times the MSE divided by the chi-squared alpha over 2 with n minus a degrees of freedom. I'll have sigma squared in the middle, and then I'll have n minus a times the MSE divided by the chi-squared 1 minus alpha over 2 n minus a. And that is still equal to 1 minus alpha, and therefore my confidence interval is this portion in the center. This is my 1 minus alpha times 100% confidence interval for sigma squared. Okay, so I have n minus a over times MSE over the chi-squared alpha over 2 with n minus a degrees of freedom. And the upper limit is n minus a times the MSE over the chi-squared 1 minus alpha over 2 n minus a. So that is my confidence interval for sigma squared. Now, when we talk about the confidence interval for sigma tau squared, then we need to remember what we just noted that n minus a times the MSE over sigma squared has a chi-squared with n minus a degrees of freedom. Likewise, a minus 1 times MSTRT divided by sigma squared plus sigma of tau squared, that has a chi-squared distribution with a minus 1 degrees of freedom. Okay. Now, we need to recall that the estimate of sigma hat tau squared was the MSTRT minus the MSE over n naught. Okay. And this is a linear combination of 2 chi-squared random variables. And we could say that this is u1 times chi-squared a minus 1 minus u2 chi-squared n minus a degrees of freedom. And if we do the algebra, we'll find that u1 is sigma squared plus n naught sigma tau squared over n naught a minus 1, and u2 is equal to sigma squared over n naught times n minus a. But we have an issue. We cannot get this in a closed form expression. Remember the distribution of the chi-squared random variable. And so if we want, when we try to find probability or take integrals, we end up with that chi-squared distribution. And we end up with an integral we can't write in a closed form. Okay? So we have this issue. We cannot determine the exact confidence interval for sigma tau squared. Now, we're not going to talk about the second method, which is using the maximum likelihood estimators and the restricted maximum likelihood estimation method. They're very technical, and we don't need to understand the depths of that. But with this method, we can numerically estimate sigma hat tau, or sigma tau hat. Now, this is an estimate or approximation, and it's using numerical methods. So that means that we plug in a value, and then we come up with an estimate, and then we do another, we use that estimate to get closer to the real estimate. And so we look for that to converge, and when it converges, we say that we are within a certain amount. Then we say that we have found an estimate. Okay, so we will see that we can find those estimates, but we can't calculate them directly. What we can do, calculate an exact expression for is we can construct an exact expression for this ratio, sigma tau squared over sigma tau squared plus sigma squared. Now, remember that the variance of Yij is equal to the variance of Yij is equal to alpha, I'm sorry, wrong class. This is the variance of mu plus tau I plus epsilon ij, if we want to write it as the treatment effects model, or the effects model. And mu is a constant, and so this is going to be simply the variance of tau I plus epsilon ij, because the variance of a constant is always 0. Now remember that tau i's here are random variables, and also that tau I is independent of epsilon ij for all I and for all j. That means that this variance is equal to the variance of tau I plus the variance of epsilon ij plus 2 times the covariance of tau I epsilon ij, but they are independent, so this covariance is 0. So this is simply the variance of tau I, which is sigma tau squared, plus the variance of epsilon ij, which is sigma squared. So this is the total variation, variation in the model. Okay? So what we're doing is we're calculating this proportion. And sigma tau squared is the variation between treatments. Okay, between treatments. So we're finding the proportion of variation between the treatments to the total variation in the model. And this is called an intraclass correlation coefficient. So right here we've said the proportion of the variance of an observation that is the result of the differences between treatments. All right, so let's do the derivation of the confidence interval for this intraclass correlation coefficient, this ratio. first off, remember that the MSTRT, the mean square treatments, is independent of the MSE. And that is why we can use the F statistic for the test. It's because it's a ratio of independent chi-square random variables gives us an F statistic. That's something that we should know. So we can take this ratio of MSTRT divided by N naught tau squared, sigma tau squared plus sigma squared over MSE divided by sigma squared, and that gives us an F distribution with A minus 1 degrees of freedom in the numerator, N minus A degrees of freedom in the denominator. And so, once we know the distribution of this ratio, this quantity here, we can find the confidence interval. So we write the probability, again we have between the critical value f of 1 minus alpha with these degrees of freedom and f of alpha over 2 with the same degrees of freedom. Well, the area in between that will be 1 minus alpha, or the probability between those two values will be 1 minus alpha. And so what we want to do is we want to solve this for this ratio. And we have a little bit of an issue because we have N naught here, okay? And so what we're going to do is we're going to, let's see. So what we're going to do is we're going to invert this, and this, all three. So we're going to flip them. Now, when I invert this fraction, it's just going to put the denominator in the numerator and the numerator in the denominator, and the same here. And then we'll have 1 over this and 1 over this. And so this value, again, will go over here because it will be smaller. And this value, so these values will switch positions once we take them and reciprocate them or invert them. Okay? Take the reciprocal of them. So we have the probability, and now I have f of alpha over 2, a minus 1, n minus a degrees of freedom. And then I flip both of these. I have MSE over MSTRT. And then I have N naught sigma tau squared plus sigma squared over sigma squared. And then I have 1 over f of 1 minus alpha over 2, a minus 1, n minus a. And that is still equal to 1 over alpha. And now I'm going to multiply or divide by this expression. Okay? So when I divide by this, I'm going to get the probability that, and I'm going to have MSTRT over MSE times 1 over f of alpha over 2, a minus 1, n minus a. And then I'm going to have n naught sigma tau squared plus sigma squared over sigma squared. And I'm going to go ahead and rewrite this. I can rewrite this common denominator. I can write this as n naught sigma tau squared over sigma squared plus 1, because sigma squared over sigma squared is 1. And then I have MSTRT over MSE, and then times 1 over f of 1 minus alpha over 2, a minus 1, n minus a. And now I'm going to subtract 1 from all three sides, so I get rid of this. So this is equal to the probability that MSTRT over MSE times 1 over f of alpha over 2, a minus 1, n minus a, and then, minus 1. And then in the middle I have n naught sigma tau squared over sigma squared, and then I have MSTRT over MSE, and 1 over f of 1 minus alpha over 2, a minus 1, n minus a minus 1, and that is equal to 1 minus alpha, that probability. Now, I need to divide all sides by n naught so that I can isolate sigma tau squared over sigma squared. So this is going to be the probability of 1 over n times MSTRT over MSE times 1 over f of alpha over 2, a minus 1, n minus a, minus 1. I close that parenthesis. In the middle now I have sigma tau squared over sigma squared. And here I have 1 over n naught. Don't forget the naught, because if it's unbalanced, it'll be different. MSTRT over MSE. And then I have f 1 minus alpha over 2, a minus 1, n minus a, minus 1, that, and then I have the overall bracket, 1 minus alpha is the total probability still. So algebraically rearranging what's inside the probability function does not change the probability. Okay, so this gives us a confidence interval for sigma tau squared over sigma squared. Okay? So this is the CI for this ratio, but I want the CI for sigma tau squared over sigma squared plus sigma tau squared. That's what I want. Okay. So what I'm going to do is I'm going to call L, let L equals 1 over n naught MSTRT over MSE, 1 over f of alpha over 2, a minus 1, n minus a minus 1. And u is equal to the upper number, 1 over n naught MSTRT MSE, the denominator, 1 over f of 1 minus alpha over 2, a minus 1, n minus a, minus 1. Okay. And now I'm going to have to do some algebra. To get the ratio that I want. So what we have here is we have sigma tau squared over, I'm going to move this over to the side. So a little bit of algebra, and we're going to have to use a separate sheet of paper here. But we have L is below sigma tau squared over sigma squared, and U here. So now, what I'm going to do is this is equation 1, and then if I add 1 to all three sides, I'll have sigma tau squared over sigma squared plus 1, U plus 1. And I can rewrite this as L plus 1, and then I can say sigma tau squared plus sigma squared over sigma squared, and I have U plus 1. Now, what I'm looking for, the ratio that I want is for sigma tau squared over sigma tau squared plus sigma squared. That's what I want. And this is not it. And this is not the reciprocal of it either. So I'm going to clean this up a little bit. So this is sigma squared. Okay. But I'm going to call this equation number 2 now. Okay. And now, that's equation number 2. Now, so that follows. Now, this, I can also say, I can now solve this for sigma tau squared. So I have sigma squared L, sigma tau squared in the middle, and sigma squared U. Okay. Now remember, I want sigma tau squared over sigma tau squared plus sigma squared. So what I'm going to do is I'm going to divide all three parts of this inequality by sigma tau squared plus sigma squared. And since this is all positive, because all of these quantities are positive, I don't have to change the sign of my inequality. Okay? And now I want to rewrite this. I'm going to multiply by 1 over sigma squared in the top and the bottom. So I'm multiplying by 1 overall, but I'm going to do that across the whole inequality, all three portions. And this is going to give me L, so this is separate, so L over sigma tau squared plus sigma squared over sigma squared. And then I have sigma tau squared over sigma tau squared plus sigma squared. And then I have U over sigma tau squared plus sigma squared over sigma squared. And this becomes, I'm going to move to another piece of paper here. So this becomes L over sigma tau squared over sigma squared plus 1. This is sigma tau squared over sigma tau squared plus sigma squared. And then I have U over sigma tau squared over sigma squared plus 1. Now if I look back at equation 2 here, I have L plus 1 and I have U plus 1, and I have sigma tau squared plus sigma squared over sigma squared. And that's exactly what I have, sigma tau squared plus sigma squared over sigma squared. So that's what I have in the denominator here. And so that's sigma tau squared plus sigma squared over. So that's what I have here. Okay? So I have, and that's between L plus 1 and U plus 1. So let me rewrite that here. So I also have, so I'm going to get rid of this. So I have that, so I have L plus 1, and then I have sigma tau squared plus sigma squared over sigma squared, which is U plus 1. And so that's sigma tau squared over sigma squared plus 1. Okay? Now, let me show you a proof here. So if A is positive and is less than B, this implies that B plus A is less than AB plus B. We've added AB, which is again positive. And so the relationship, I've added it to both sides, so the relationship holds. And then I'm going to factor AB plus 1. And then I've got B, A plus 1. And now I'm going to divide both sides by A plus 1. So I get A times B plus 1 over A plus 1 is less than B. And now I'm going to divide both sides by B plus 1. And I get A over A plus 1 is less than B over B plus 1. So since these are all positive, I can use this relationship, and I'm going to take the ratio. So I have that, I have L over, and so I can simply replace that with what's less than that quantity. What's less than that quantity is L plus 1. So I have L over L plus 1, and then I have sigma tau squared over sigma tau squared plus sigma squared. And then I have U, and I can replace that with what's greater than that, which is, so I can replace this term here with U plus 1. and I have u over u plus 1. So my 1 minus alpha times 100% CI for sigma tau squared over sigma tau squared plus sigma squared, the intraclass correlation coefficient, is L over L plus 1 to u over u plus 1. Sigma tau squared over sigma tau squared plus sigma squared. Okay? So that is our confidence interval. And remember that where L, let me put a different color. So L is this equation, and U is this equation. And so we have shown that L over L plus 1, sigma tau squared over sigma tau squared plus sigma squared, is between u and u plus 1. So that is our confidence interval that we're going to calculate for that intraclass correlation coefficient. Okay. Now the last thing that we want to estimate is mu. And so mu hat is simply y dot dot bar, the overall mean of the y's. Okay? And when we look at the variance of y dot dot bar, it's the variance of, so the variance of y dot dot bar is equal to the variance of yij over n. Okay, so remember that the variance of x bar is equal to sigma squared over n. And so it's the variance of x, this is the variance of x over n. And so we're doing the same thing. The variance of yij divided by n, the variance of yij is n naught sigma tau squared plus sigma squared. And this means that so now I can take this, and this can be estimated with MSTRT. If you remember, this is estimated by the MS treatment. And so now be careful with the notation. Notice that I have a hat over the V. So this is equal to V of mu hat, and that, but it has population parameter values in there that we don't know. So we were going to estimate this. V hat of mu hat is equal to the MSTRT over n. This is another way of writing it. We have two hats here. We have the hat, the estimate of mu, and then we have the estimate of the variance, where we plug in for the variance estimates here. Okay, so this is our MSTRT, is our estimate of mu hat. And we want a confidence interval for this. It's y dot dot bar minus t alpha over 2 times with n minus a degrees of freedom times the square root of MSTRT divided by n. This is the standard error. This is the square root of the variance of y dot dot bar hat. Okay, so this is the standard error of y bar dot dot, y dot dot bar. Sorry, I have too many dots there. We'll take care of it that way. And this is the critical value. So we have a minus and we have a plus. So we've done the derivation for this earlier, so I won't do it again in the fixed effects. So this is our confidence interval. All right. So that's it for this video. In the next video, we will apply this using R. And instead of doing it by hand, we'll just use R code. And so if you have questions, come to virtual office hours. And if you need help before office hours, by all means, email me. I'll get back to you as soon as it's possible. When you email me, you need to email me a copy of your work, a copy of the problem, so that I can see what the problem is, because I don't have them memorized. And then I can see how you're approaching the work and get back to you and help you the best. So please take care of yourself and stay safe, because we want to see you next time.